students. Today we are going to be doing something remarkable. That's right. We are going to be calculating what Earth's gravitational force is. That's right. We're going to be measuring how strong Earth's gravity is. And it really doesn't require much in order for us to do this, thanks to the likes of Isaac Newton. So we're going to start off with one of these things. So I'd like you to watch it going back and forth, back and forth, back and forth. Your eyes are getting heavy. Your eyes are getting heavy. You're feeling very, very relaxed. Wake up! Okay, no, we're not trying to hypnotize you. Does anybody know what this is? This is a pendulum. A pendulum is simply some type of a mass attached to a string, a cord, a wire, something that it can hang from. And if you take a pendulum, the mass of a pendulum, and you lift it up, what's going to happen when you let go of it? Whee! Gravity pulls it down. Now, because it's attached to a string, as gravity pulls it down, it's not going to fall all the way down to the ground, but rather its momentum will enable it to swing up in the other direction, and it will go back and forth and back and forth. Now, great scientists like Isaac Newton came up with some fabulous mathematical relationships, not only between a mass attached to a string and the force of gravity, but its connection to time, which enabled pendulum clocks to be developed hundreds of years ago, keeping regular time as pendulums swinged, went back and forth. But anyway, today we're going to be using the pendulum principle in order to calculate Earth's gravity. And all you need is a pendulum, again, some type of a mass, and a string. You need a stopwatch, some way of measuring time down to the second. And you also need some type of a measuring device, like a ruler or measuring tape. With those simple things and the calculator between your ears, or if you really need help, a calculator as well, that will help you determine what Earth's gravitational acceleration due to the mass of the Earth is equal to, believe it or not. So let me explain to you how we're going to do this. So I explained to you before what a pendulum is. And a pendulum is a mass on some type of a string that's allowed to swing back and forth. And it's allowed to swing back and forth because when you let it go, gravity is going to be pulling it down. But the string prevents it from going all the way down to the ground. So it's just going to go back and forth and back and forth. Well, by collecting only a certain pieces of information, thanks to Isaac Newton, we're going to be able to calculate Earth's gravity. So here are the things that you need to do. First, you're going to measure the length of the pendulum. Now, in the laboratory, we have a ginormous pendulum in the middle of the room, and we're going to be using that ginormous pendulum in order to take our measurements today. We'll be doing this as a class, but if you are remote, then you can use the data that we have collected. So in your books, you can write down that the length of our pendulum is 2.48 meters long. That's from the ceiling down to the bottom of the mass. So that's a pretty long pendulum. Next, we're going to measure the time it takes using a stopwatch. We're going to measure the time it takes to swing back and forth 10 times. That'll just make our math easier. So a full swing is back and forth, back and forth. A full swing is back and forth. That's one full swing. So 1, 2, 3, etc. So the time it takes our ginormous pendulum to swing 10 times is 32 seconds. Now, the next piece of information we need is to determine what is called the period. The period is basically the length of time for an individual swing. So the way we determine the period is simply to take the time for 10 swings and divide it by 10. And that gives us 3.2. It was 32 seconds for 10 swings divided by 10. You just move the decimal place once over to the left, and that gives us 3.2. And now, with that information, we are ready to plug in the numbers. We're going to use that information. But as we do, I want you to remember PEMDAS, something you've probably learned in math class. PEMDAS. Does anybody remember what PEMDAS stands for? Parentheses, exponent, multiplication, division, addition, and subtraction, or in other words, the order of operations. So this may look very intimidating to you right now. You don't have to memorize this formula. This formula was developed by Isaac Newton, and we're going to be using this formula. We won't even talk about how this formula was derived. You can save that till 8th grade when you learn algebra as to the details of this. But the first thing that we need to identify is what these letters are. In this equation, the big G stands for gravity. That's what we're looking for. And then we have 39.5 times L, and the product of those divided by T squared. Well, what is L and what is T? L is the length of the pendulum, and T is the period of the pendulum, the time per swing. And you've already collected that information. So we're going to first substitute or plug in our values that we measured earlier, and this is what we get. G is equal to 39.5 times 2.48, all of that divided by 3.2 squared. Again, don't be intimidated by the mathematics. We just follow PEMDAS. So the first thing we want to do is look for any parentheses. Is there any mathematics we can complete within parentheses? And the answer to that is yes. The 39.5 times the 2.48 are within a set of parentheses. So that's what we will take care of first. And by multiplying those two numbers, you get 97.96 divided by, and we haven't done anything yet, the 3.2 squared, so we just continue to write it down, the 3.2 squared. Now that exponent there is the next thing in PEMDAS. The exponent of 2, which we read as 3.2 squared, simply means that we take that number and multiply it by itself. So if you do that, our next line will read, and we just copy down the 97.96, will then be divided by 3.2 squared, which is 10.24. What's next in PEMDAS? Well, the M and the D. The M and the D is the multiplication and the division. And right now we've got a division problem. So we're going to take 97.96 divided by 10.24, and we get the answer 9.57. Now, for the purposes of this activity, we're going to round your answer to the nearest whole number. So 9.57 rounded to the nearest whole number is 10. And so our answer is 10 meters per second squared. So what does that mean? Well, first of all, that's the right answer. If we wanted to be really precise and use more precision equipment, the actual answer is 9.8 meters per second squared. But as I said, we're just rounding to the nearest whole number here. So 10 meters per second squared is pretty much our answer. So again, what does that mean? What that means is this. If we were to take an object and drop it, and there was nothing attached to it, and assume there's no atmosphere on Earth, so we drop something, it's going to fall at a rate of 10 meters per second squared. Again, what does that mean? Well, it means every time that object drops 10 meters, it's only going to take a second to do that. And the next 10 meters, it's going to be dropping even faster. In other words, it's going to accelerate and keep on getting faster and faster until that object strikes something like the surface of the Earth, for instance. So if you were to go skydiving and jump out of an airplane, thankfully we do have an atmosphere and the air will slow you down a little bit. And if you deploy your parachute, that'll slow you down even more until you hit the ground. But if there was no atmosphere and there was no parachute, you would just continue to accelerate at a rate of 10 meters per second squared. That is the answer to our lab activity. So in summary form, here's what you did. You gathered the length and determined the period of a pendulum. You plugged in your numbers, you did the math, and you came up with an answer. Now, if you're in the class today, you are going to be performing this experiment with different pendulums. Our pendulums will have different lengths. And we're going to have a little friendly competition here and see what kind of answers you come up with using pendulums of different lengths. So, that being said, we're going to need the rest of our time to get busy. So for now, I'm going to say bye-bye.